Hey everybody, my name is Kelvin and welcome back to my channel. Today, I want to go through 5 Python tips and tricks that you probably didn't know. Without further ado, let's get started. Our first tip is multiple assignment and one-line swapping. What is that? Python lets you assign several variables in a single statement, and it also lets you swap variables without using a temporary variable. Let's take a look at an example. Our example 1.1 is assigning several variables at once. We have a before and after setup. In the before version, we take the very direct approach, as in we assign each variable on its own line and then print them. This is the style most people will learn at first, and it's pretty easy to follow, but really there's no visual hint that these 3 values are a single bundle of related information. We can run it and see what it prints. And we get Alice, 21, Boston. It works fine, but each assignment is separate, so the connection between them is implicit rather than obvious. Let's take a look at the after version. In the after version, our goal is the same, but the approach is different. We're going to be treating these 3 values as a small package that we can unpack into 3 variables. It's more compact and reads almost like a single sentence. The code should still print the same 3 values, but using a single assignment for all of them. If we print it, we get the exact same output. We pack 3 values on the right, and we unpack them into 3 variables on the left. It's more compact and makes it clear that these values belong together. Our example 1.2 is about swapping 2 variables. We want to swap the values of 2 variables, A and B. The code should know that A and B changed places when we print them. In the before version, we use the classic textbook approach to swapping. We introduce a temporary variable, copy one value into it, overwrite the original, and then copy from the temporary variable back. This is the pattern you would use in almost any other language that doesn't support tuple unpacking. When we run the code, we should expect to see A:20 and B:10. The swap works, but it takes 3 lines and an extra variable to express a concept that is logically pretty simple. In the after version, we use Python's multiple assignment to swap these 2 values directly. Instead of manually shuffling values around, we can rely on Python to handle the temporary storage for us. The code should still show that the 2 values are swapped. After we run this, we should get the same exact output. And we can see that it indeed does. Python evaluates the right side as a pair, B and A, and then unpacks it into A and B. It's shorter, easier to read, and avoids the temporary variable altogether. So the benefit here is multiple assignment keeps related values together, and it makes common operations like swapping both shorter and less error-prone. Our second tip is extended unpacking with the star operator. This lets one variable on the left side of an assignment collect multiple elements from a list. It's useful when you care about the first and last elements and want the middle grouped together. In our example 2.1, we want to split a list into 3 parts. The first element, everything in the middle, and the last element. The code will print each of these 3 parts so we can see what they contain. In the before version, our approach is to manually slice the list. We can index 0 for the first element, index -1 for the last, and a slice for the middle. It's straightforward, but we have to remember 3 separate expressions, and they all refer back to the original list. When we run this, we should see first, 10, middle, a list of 20, 30, and 40, and then last should print 50. We get the correct result, but the structure is expressed through indexing and slicing instead of just being visible in one place. We have a more elegant solution for this. The approach is to describe the structure of the list directly in the assignment. One item at the start, a group in the middle, and one item at the end. The star variable here is our catch everything in between placeholder. If we run this, we should expect to see the same exact thing as we did up here. And we can confirm that they both functionally are the same. The first variable gets the first element, last gets the last element, and star middle will absorb everything in between into a list. So one line encodes the shape of the data in a very visual way. In our example 2.2, we want to take the head of the list and ignore the rest. So in this example, we only care about the first element. The code should print that first element and clearly show that the rest is being ignored. In the before version, our approach is just grab index 0 and then just forget about the rest. That's totally fine, but it hides the fact that the list contains more elements, which we are discarding. When we run this, we see head only 10. The remaining values are never mentioned. Now, in the after version, our approach is going to be a bit more expressive. We still take the first element as head, but we also explicitly capture the rest into underscore, which we treat as unused. That makes the intent clear. There is more in the list, but we're purposely ignoring it. The code is functionally the same. It'll still only just print the head. Head still gets the first element, and star underscore collects the remaining element into a throwaway variable. It tells the reader that the list has a head and a tail, but really only the head matters here. Extended unpacking lets you encode first, middle, last, or head and tail directly in the assignment, instead of scattering that logic across multiple lines. The third tip that you may not have known is the for else for search. You either find what you want and exit early, or you reach the end without finding it. For else lets you express both outcomes in a single structure. For our example 3.1, we want to search a list for a target variable. The code should print found it if the target is present, otherwise it should print target not found. In the before version, our approach is to maintain a manual flag that tracks whether we have seen the value or not. We assume it is not present at first, then flip the flag and break if we find it. After the loop, we inspect the flag to decide which message to print. When we run it, we should get found it and 12. Because the target is present, we set found to true and skip the not found message. In the after version, the idea is the same, but we let the for loop structure itself track success or failure instead of carrying a separate flag. We rely on the fact that hitting break means we found it, and reaching the end means we did not. The code should still print found it when the target exists, and target not found when it does not. When we run this again with target equal to 12, we again get found it 12. If we change target to a value not in the list and ran it, the loop would finish without hitting break, and the else would print target not found. The benefit of this tip is that the for else keeps the search and fallback logic together in a single block instead of scattering it across a flag and a separate if. Tip 4 is using any and all for conditions. Our tip 4 is using any and all for conditions when you want to ask questions about a list. Any answers the question of, is there at least one element that passes this test? And all answers, do all elements pass this test? You can pair them with a small expression inside a generator. Our example 4.1 here answers the question, does the list contain an even number? In this example, the code should print a Boolean answer. Our approach here is to track a Boolean flag, and we start by assuming that there is no even numbers, then we scan the list, flip the flag when we found one, and break early to avoid doing any extra work. When we run this, we should get has even true, because we know that 8 is even. We have a more elegant solution. In the after version, our approach here is to turn that logic into a single expression. Instead of manually managing a flag, we can ask Python the high-level question, is any number even? The code will still print a true and false answer. The generator inside any produces true for even numbers and false for odd ones. Any returns true as soon as it sees one true, which matches exactly what we want. Our second example here, we want to answer the question, are all scores above some certain threshold? In this example, we want to make sure that every score on the list is at least 80. The condition should print whether that condition is satisfied. In the before version for 4.2, our approach is similar to the previous example, but in reverse. We assume everything is fine, then scan for a single bad value to disprove that assumption. If we find a bad score, we flip the flag to false and break. When we run this, we should see that our all high variable will remain true because all the elements in the list are higher than 80. Again, we have a more elegant solution for this. Our approach is again to let Python handle the overall question in one call. We phrase the requirement as a condition and ask, do all items satisfy this condition? The code will still answer whether every score meets the 80 threshold. Running this will again give us true. It captures the all must pass idea without explicitly managing a loop and a flag. The benefit here is that it turns it into a one-liner check instead of managing the manual flags and loops by hand. Tip number 5 is using slicing to copy, reverse, and step through sequences. Slicing uses this pattern right here. Sequence, index, start, stop, step. If you leave parts empty, Python fills in defaults. This lets you replace many small loops with a single clean slice. In our example 5.1, we want to create a separate copy of a list so we can modify one without touching the other. The code should print the copied list to confirm it matches. In the before version, our approach here is to build a new list manually. We start with an empty list and append each element from the original one by one. It's an explicit approach, but it's also a bit verbose for such a common operation. When we run this, Python prints copy 10, 20, 30, 40, and 50. We have a new list with the same exact contents. However, in our after version, our approach is to use slicing to ask Python for a copy of this entire list. We don't really care about the loop details, and we just care about the result. Our slice right here, data with a colon in between, means from the start to the end, and it returns a new list with the same elements. It's a concise way to make a shallow copy. In example 5.2, we want to create a reverse version of a list without changing the original. The code should show the reverse list. In our before version, our approach is to reverse the list by walking indices from the end to the beginning. We use range with a negative step and manually append elements in reverse order. It works, but it is pretty easy to mistype the range boundaries. When we run this, we should get the reverse list, 50, 40, 30, 20, and 10. In our after version, our approach is to again let slicing do the work. Instead of manually stepping backward, we ask for the list with a negative step. We leave the start and stop blank, and the step is -1, which means walk backwards, which returns a reverse copy without any explicit loops. In example 5.3, we want to create a new list that contains every second element from the original list. The code should print the resulting list so we can see which items were picked. In the before version, our approach is to use a for loop with a step size of 2. We manually compute the indices we care about and append each corresponding element into a new list. Again, it's explicit, but the intent is buried in the range parameters. When we run this, we should see 10, 30, and 50. We have a more elegant way to approach this. Our after approach is to tell Python to take the whole list, but step through it in jumps of 2. Slicing already understands that pattern, so we can just use the step parameter. The code should give us the same exact 10, 30, 50 list. And we can confirm that it does. In example 5.4, we want to reverse a string, so the code should print the characters in the opposite order. In our before version, our approach is to use a loop that walks through the string in reverse and gradually builds a new string character by character. Again, conceptually very simple, but not compact at all. When we run it, we should see the reverse of Dijkstra. In our after version, our approach is to reuse the same slice pattern that we used on the list. Strings in Python are sequences too, so slicing will work the same way. The code should still print the string backwards. We have the same result, but we have less code, and the slicing pattern is easy to recognize once you've seen it a few times. Slicing gives us a compact vocabulary for working with sequences, so you can copy, reverse, or step through data without having to write loops every time. So these were 5 Python tips and tricks that you can start using today. The first was multiple assignment and one-line swaps to keep related values together. Our second tip was extended unpacking with the star operator to fill out first, middle, and last parts of a list. Our third tip was the for-else structure for clean search logic with a natural fallback. Our fourth tip was using any and all to express questions like, does any item pass this test, or do they all pass? And our fifth tip was slicing patterns like bracket, bracket, colon, -1, and bracket, colon, 2, bracket to copy, reverse, and stride through sequences. If you guys are interested in the code that I used today for our demonstration, I have linked the GitHub repository down below in the description. Thank you all for watching. Don't forget to comment, like, and subscribe if you'd like to see similar content, and I'll see you guys in the next video. Thanks for watching.